Alright, numbers 161 and 162 deal with further applications of that percent by mass formula, which again, just to remind you, so percent by mass is equal to the mass of the part divided by the mass of the whole times 100%. Mass of the part divided by mass of the whole times 100%. And we can use mass percentage to figure out a whole bunch of things. So in number 161, you're given the mass percentages of barium, oxygen, and carbon in a compound, and you're asked to find out what the empirical formula of that compound is. When you want to go from mass percentage to the chemical formula, you can follow basically the same steps every single time. So your first step is to assume that you have 100 grams in total. So if you have 100 grams in total, for instance, for barium, if you have 69.58% barium, you'll have 69.58 grams of barium. Right? You can basically just change the percent after the number to grams, and that'll give you masses. After you get your masses of each element, so in this case, that's our second step right there, you can figure out how many moles of each element you have. And you do that by dividing these masses by the molar mass of each element here. So mass to moles, molar mass. After you get your moles, what you want to do is you want to look at the moles of each element and try to figure out which one is the lowest number. So in this case, right, our 0.5067 is the lowest number of moles we have here. After you figure out which one has the lowest number, you want to divide all of these numbers of moles by that number. So you're going to divide 0.5067 by 0.5067, divide by 1.5.20 by the same number, and divide 0.5070 by the same number. If you do that, you should get numbers really close to whole numbers. And if they're not close to whole numbers, they may be close to something 0.5. But if it's close to a whole number, you can round. So you'll round to get this whole number. When you divide 0.5067 by itself, you get 1. When you divide 1.520 by that number, you get close to 3. And when you divide 0.5070 by 0.5067, you get a number close to 1. These numbers will act as the subscripts for each element in your chemical formula. That'll give us the following chemical formula. It'll give us BaCO3. You may get your elements out of order here. If you realize that this is an ionic compound because it's got a metal and some nonmetals, you know barium's got to go first, and then you got to figure out how to organize your carbon and oxygens. So if you know that CO3 is carbonate, you can remember to put your C before your 3 O's, and the formula for this is BaCO3. You get barium carbonate. Alright, in 162 we're working in the opposite direction. In this case we're starting with formulas and we want to know percent by mass. We want to know percent by mass of iron in each of them to figure out which one of these compounds has the highest percent by mass of iron. So in this case, you figure out the mass of iron in each of them. So for instance, FeS2 has 1 iron. So you can just use the molar mass of iron in the top of this fraction. And you can determine the total mass. That's just the molar mass of the compound, right? You take your iron, you add 2 sulfurs to it, you get 119.979 grams. Multiply that by 100, that'll give you your percent by mass of iron in that compound. Right, in Fe2O3, we've got to account for there being 2 irons. So that's the molar mass of 2 irons in the numerator, and in the denominator, we've got the total molar mass for the compound. FeCO3, you do the same thing. You've got 1 iron divided by the molar mass of FeCO3. Those will give you the percent by masses, and it'll end up that our Fe2O3 has the highest percent by mass of iron. Problem 164 is a lot like problem 161, except we're adding another step here. Right, we're starting with we're starting with percent by masses of 3 elements. Instead of just figuring out the empirical formula, you want to figure out the molecular formula. So the difference between an empirical formula and a molecular formula is that the empirical formula shows the lowest whole number ratio of atoms of each element. Lowest whole ratio. Molecular formula, on the other hand, gives you the actual number of atoms of each element. To determine the molecular for a compound when you're starting with percent by mass, the procedure is really similar to determining the empirical formula, but we add another couple steps onto the end. You need to figure out the molar mass of your empirical formula, and you divide the molar mass of the molecular formula by that number. So you do molar mass of molecular by the molar mass of the empirical. That'll give you a whole number. We'll call that whole number n. You then multiply all of the subscripts in your empirical formula by that number n. So if you look at this problem here, right, we've got percent by masses of carbon, hydrogen, and oxygen. Our first step is assume we have 100 grams. That'll give us the masses of these things. We can then use the molar masses of each element to give us moles, divide by the smallest number of moles to give us the subscripts. So in this case, our empirical formula has subscripts of 27, 44, and 1. Okay, if we want to figure out the molar mass of this formula, we use the molar masses of carbon, hydrogen, and oxygen, multiply them by those subscript numbers to give us the total molar mass, 384.648. In the problem, you're told that the molar mass of this compound as a whole is 384 grams. So that's the molar mass of the molecular formula. If you divide the molecular by the empirical, like we do here, you get 1. So it ends up that the molecular formula in this problem is the exact same as the empirical formula.